Okay, so this is chapter 2, History of Astronomy. Astronomy in the Renaissance. This is both the notes and the lecture. Okay. Um, and we start out with Copernicus. Copernicus was a Polish astronomer, and Copernicus is the guy that really pushes the heliocentric model, that model with the sun at the center and all the planets orbiting the sun. Copernicus, though, when he's put under the pressure, Copernicus backs off and says, "Well, maybe I'm wrong in that," and da 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 da, because he doesn't really want to go against Catholic Church in that. So he um, he really pushes that heliocentric model, and then he kind of backs off. Um, Tycho Tycho is a wealthy person, and Tycho has the money to buy and build all kinds of fancy um, equipment for looking at the stars and looking at planets and that. He makes big. He doesn't have a telescope. He has big sextants. Those are the things they used to use to study the ocean, to navigate the ocean. He made big protractors. And when I'm talking big, these things were, 6 feet tall. And he would look at the stars. He would put it in front of him and look at the stars with the protractor and all this kind of stuff. Now, he had the money and he could do this stuff, but he didn't like to crunch the numbers. And there is a lot of number crunching in astronomy and figuring out different times, how long it takes the planets to show up every night, how far they move across the sky. He was into that, but not into the math of how to figure out why they do this. So here's his buddy, his understudy, guy he had working for him, Kepler. And now Kepler, the reason Tycho keeps Kepler around is because Kepler's the mathematician. He's doing all the math while Tycho's doing the observations. Okay. So Kepler's crunching the numbers. Kepler has 3 laws. Kepler's laws, you'll see them when you read this. Make sure you guys read this. Okay. I'm just adding to what's going on in the reading. Kepler has 3 laws. Law 3 is the dandy. It's the best law there is. The first law has to do with the elliptical orbits. And then the third law, the most famous law, is the farther a planet is from the sun, the longer it takes to orbit the sun. Okay. And he mathematically proves it. Believe it or not, this distance, if you take this distance from this planet to the sun and cube that number, a cubed, or the distance cubed, equals the orbit squared. Okay. So if you take this distance here and cube it, it is equal to the orbit time squared, or the orbit period. Again, look that up in your book. It's really, really important. Why is that important? When we're looking at planets with things like the Hubble Space Telescope, and we find a planet orbiting another star or its sun, if we can measure the distance, or if we can measure its orbital time, we can decide whether or not it's a habitable planet. Does it have the same distance? Does it have the same period as the Earth? If it does, then possibly it could have life on that planet. So it's very important to know Kepler's third law. Of course, we should be knowing everything about Galileo at this time. All right, Galileo's the man here. He is, you can see him with his telescope, and we know his story. Okay. Isaac Newton. Now, Isaac comes along and he takes Galileo's work. And Isaac Newton's probably, I don't even know if there's another scientist like him. He's the best ever, no doubt about it. He is the man when it comes to um, astronomy. All right, he comes up with the idea of gravity, and that's what holds the planets together. He improves the telescope. He really starts crunching numbers. He even invents a new math. He has he has questions that can't be answered with algebra. So he sits down and he said, "There's got to be a way to answer these questions," and he invents calculus. All right. Um, this is from a. I'm using these slides from another presentation I gave, but it fits well with Newton's law of universal gravitation. We've discovered new planets: um, Uranus, Neptune, Pluto, and planets around other stars. Okay. Um, we discover these by the use of Newton's gravitational um, law of universal gravitation. And that law works everywhere. It doesn't matter what you're looking at, it works the same way every place in the universe. Here's his book on optics. After he was done with his astronomy work, he started working with optics and the nature of matter and heat. We will talk more about black body radiation. Um, and the Kelvin scale gives us these different colors. I'll just go into the black body right now, real quick. So, black body radiation. Um, I can't think of the scientist's name right now, but he was looking at the stars and he had to have some blacksmith work done. And you know, this is back in the days of the horses and stuff. So he's getting blacksmith work done, and he's looking at the metal as a blacksmith heats it, and he notices it going through the colors. It starts in red, orange, yellow, green, and then the purples. Real hot are the blues and the purples. And he thought, man, when I look at stars, if I use what I've read in optics and I apply that to the stars, if I could measure the heat off of the um, piece of black metal that the blacksmith is using, I can figure out the temperatures of stars. And that's that's how we know how hot a star is, because of this experiment where they measured the different colors of the different heats coming off the different colors. So when we look up at the sky at a star or our sun and we see what color it is, our sun's this yellowish color right here, 6,000 Kelvin. We know that the surface of the sun is 6,000 Kelvin. If we were looking at another star in the sky that was more red or more blue, we would know what the temperature would be by him measuring black body radiation curves. And here, of course, is the Kelvin scale. Any questions about this? Let me know. Hopefully, this helps you with your homework. Make sure you read it. Have a great day.